We're going to look at gravitational energy when you don't have a constant gravitational field, so applying the ideas of universal gravitation, and then we can use that to figure out the escape velocity needed to fly away from a planet of given mass and radius. So let's get right to it. Gravitational potential energy, previously we just said that this was equal to mgy, and we said that we can call any y to be zero potential energy, and really all we cared about was the changes in gravitational potential energy, mg delta y. But this doesn't work if little g is not constant, so we can derive a new expression from universal gravitation, and we'll start out looking at the work done by the gravitational force. So that is going to be F dot, we're going to call it dr instead of dx because we've got r's in our universal gravitation equation. You could put x's in there, it's all the same. So this works out to be, we're going to have a negative sign because the force is pointing in the opposite direction of our r vector. So we're going to have g m. I'm going to do one small m for the object and a big M for the mass of the planet, so typically Earth. And then we've got over r squared dr. And we'll say this is from some position r1 to another position r2. So we go ahead and integrate that. We can pull out the gm stuff. So that is just the integral of 1 over r squared dr, and that becomes gmm over r from r1 to r2, which gives us gmm over r2 minus gmm over r1. Oops, squared that. Should have been a 2 down there. Sorry. Alright, now because we know that gravity is a conservative force, we can also set the work equal to the negative change in potential energy, or the change in potential energy equal to the negative work done. And by the way, this is the work done by the gravitational force. If it's some force like a rocket booster or something, then the signs change, right? Anyway, so we end up with negative gmm over r2 plus gmm over r1, and this equals u2 minus u1 because that's our change in potential energy. And just like before, we could set any location to be zero gravitational potential energy. We can do that again, but we kind of do something kind of opposite of what we do here. Here we often set ground level to be 0, so kind of the lowest point that you're concerned with we set to be 0. Here we set the farthest away point possible to be 0. So we say when r1 equals infinity, then we call the gravitational potential energy out there to be 0. If that's the case, then this is 0, and since we've got an infinity in the denominator here, this goes to 0, and so we end up just with the expression u2 equals gmm over r2 with the negative sign. And we can go ahead and get rid of the 2's now because it's just arbitrary, whatever location that is. And so we have this as our expression for gravitational energy when the gravitational field is not constant. So we're going to say that we always have negative potential energy except when we go all the way out to an infinite distance from the planet or whatever we're concerned about. And there's a reason why we do that. Because we consider this what we call a bound state. So it makes sense to think about having to put energy in to remove an object from the surface of the Earth or some other planet or star. And we do something similar with electrical potential energy. If you have an electron orbiting a nucleus of an atom, in chemistry, if you've calculated those energy levels, they have negative numbers because of this same idea that you need to put energy in to remove it. But it still follows the same logic we had before, where if you're moving away from Earth, here you are in your rocket ship moving away from Earth, gravitational energy is increasing, and if you're moving toward Earth, because R is getting bigger, which makes this smaller, which means you're getting less negative, so it's still increasing. And if you're moving toward Earth, then it is still decreasing. So all of those things still follow. Alright, let's look at an example. If we want to drop a film canister, you guys might not know what film canisters are, but they used to be these little cylinder things that film would come in. Anyway, you allow it to drop from a rocket that is traveling fast, high above Earth's surface, and we want to find its speed before impact, and we're going to ignore air resistance. So we're going to use our new definition of gravitational potential energy. So for the rocket, the initial energy of the film canister is the kinetic energy, because it's moving with the rocket, so it has this speed initially. And it also has some gravitational potential energy, some initial amount. When it hits the ground, it's got some new kinetic energy, we'll just call it K. And we can't say that it's gotten rid of all of its gravitational potential energy, because we're now going to say it has negative gravitational potential energy. And so that doesn't go away when you're at the surface of the Earth. It goes away when you go infinitely far from the Earth. Alright, so we're going to have 1/2 m, call it V naught squared. Make sure to have a negative sign in here, G m, capital M over R. Be careful not to square that. It's squared for the force, not squared for gravitational potential energy. And then we've got 1/2 m final velocity squared minus G m, I guess I'll call this R naught squared, or R naught, not squared. Anyway, GMM over R. Then we can go ahead and cancel out the masses of the object. And so we're going to have 1/2 1800 squared minus G times the mass of the Earth, 5.97 times 10 to the 24th. And we've got to be careful with our R's here. So it's that far above the Earth's surface, but R is taken from the center of the Earth. So the radius of the Earth was 6.38 times 10 to the 6th meters. Let me double check my notes. Yeah, that's right. Now this is in kilometers, so if I add 3 more zeros to turn that into meters, I can make that 1.6 times 10 to the 6th. That whole thing is my denominator. Equals 1/2 V squared. That's what we're solving for. Minus G, I'm not going to rewrite M. This R here is when we're on the surface of the Earth. So we plug in this guy, times 10 to the 6th. And I'll spare you the algebra from this point, but we end up with a speed of 5,317 meters per second. One other thing you might ask is, well, this velocity was heading in the other direction. Why would we include that? Well, it still has that energy, and so if it's released, it's going to keep going outward for a while, and then it will slow to a stop, and then it will come back to the original spot, and it will have that same speed heading in the other direction, so we can just count that as the kinetic energy. That's one of the nice things about energy, is directions of things like velocity do not matter. By the way, if we did this the old way, we could have said the initial kinetic energy plus the initial gravitational energy equals just the final kinetic energy, because we could have called the surface of the Earth the location of 0 gravitational energy, and we'd have 1/2 mv naught squared, and this would just be mgy equals 1/2 mv squared. And plug in the numbers like this, plugging this guy in here for y and 9.8 for g, and you will get the wrong answer, surprisingly. And think about, should it be faster or slower than this, by the way? And hopefully you thought it would be faster, because out there far away g is little g, anyway, your gravitational acceleration is less, so you won't be accelerating quite as much as if g were constant. This works out to be, what did I write down, 5,882 meters per second, so a bit faster. This one is not accurate. So, alright, one other concept, the idea of escape velocity. which is great fun to think about. In this case, this is often useful to figure out how much energy it takes to leave a planet and other such quantities. So if we think about, if I'm on the surface of the planet and I want the object to escape that planet, it's going to need some kinetic energy on the planet. It's got some negative gravitational energy to begin with, and in order for it to have zero gravitational energy, it has to go all the way out to infinity, and at that point we could say that it has no more kinetic energy either. We'll say that we want just enough kinetic energy so that we run out of kinetic energy, we run out of velocity when we reach infinity. So we can set this total energy equal to 0 because this guy's going to be negative. So 1/2 mv squared minus gmm over r has to equal 0. So basically the potential energy equals the kinetic energy, and then we just solve this guy for velocity. The masses cancel out, so the mass of the object doesn't matter. By the way, we're ignoring air resistance with this. With air resistance, you'd have to be traveling even faster to escape the gravitational field of a planet or a star. So you end up with V escape equals square root of 2gm, where this is the mass of the body you're trying to escape, divided by its radius. So there's your formula for escape velocity. I think it's easier to memorize this idea here than to memorize that formula, or just set the two equal to each other and solve for v. Let's look at a couple of examples of this. We want to compare the escape velocities of Earth and the Moon. So first of all, let's say the escape velocity from Earth, root 2gm over r. Here's all the information we need. So we're going to have root 2 times 6.67 times 10 to the negative 11th. Mass of Earth, 5.97 times 10 to the 24th. Trying to go fast. I know you guys have lots of important things to do. Radius of the Earth, 6.38 times 10 to the 6th. Plug that baby into your calculator and you get an escape velocity of 11,173 meters per second, which is around 25,000 miles per hour. And I will mention, with escape velocities, this is how fast you would have to launch something like an initial velocity where you weren't pushing on it anymore. So this is like how fast Superman would have to throw a baseball in order for it to leave Earth. This isn't how fast rockets have to go because they have forces continually acting on them. They don't achieve speeds like this in the Earth's atmosphere. Okay, so now let's look at that for the Moon. I won't write it all out again. You just plug in these numbers instead, and it turns out to be about 2,374 meters per second. So if we're going to compare these, we might want to take a ratio. So VE to VM, 11,173 over 2,374 works out to be a ratio of 4.7 times more speed to escape Earth. And we could have found this ratio a bit simpler, right? We could have put this equation for the Earth over that equation for the Moon, and everything would have canceled. Well, the 2 and the g would have canceled out, so we would have had root m over r over root m over r. Okay, so there's kind of the answer to part A. Part B, we want to compare the energies needed. So the energy is the kinetic energy, 1/2 mv squared, where we plug in either of these velocities for v. Problem here is the energy depends on the mass of the object, and we're not looking at a specific object, or they didn't give us the energy of these rockets. But thinking of this ratio idea, for the energies, it could be the kinetic energy on Earth compared to the kinetic energy on the Moon. Everything's going to cancel out except for the ratio of their velocities squared. And since this is the ratio of their velocities, all we need to do is take that, square it. Turns out you need 22 times more energy to escape the gravitational pull of Earth than you do